All right. Okay, so, well, today we're supposed to pretty much finish the stuff, okay? Because remember, the last homework assignment, which is due Tuesday, December 15th, remember, it's the end of day midnight after the last day of class, which is our last homework question session, right? The last day of class is Monday, December 14th, and we're going to finish discussing the homework then. The homework's due the following day, as usual, Tuesday, December 15th, end of day midnight. Lessons 33 to 43, a whole lot of stuff here, okay? And we're going to finish the stuff over here. Some of these, like lesson 39, are optional sections, but we're going to finish up today. Well, actually, lesson 43 on correlation and regression, we're going to talk a bit about that on Wednesday as well. And we'll, of course, start the homework on Wednesday also. So some of this will actually bleed over here. Also, I am finishing up the homework 3 uh, grading, and I should be done with that by tomorrow. Okay, so any questions before we finish the topics for, well, almost finish. Lesson 43 will bleed over. Any questions before we finish the topics for today? Any questions? All right, so let's go ahead and proceed then. Okay. All right, so all right.
Hi everyone, we're going to crunch down one book chapter into one lesson. Lesson 39, hypothesis test for two populations. How do we compare two populations? Now, this is a really big topic, but my feeling is that if you understand the philosophy of one population or one sample hypothesis test, then you should be able to extend these ideas to this lesson, and you should be able to pick this stuff up. I don't want to bore you with additional details when the key is really the fundamental philosophy of hypothesis testing, and we've done that. Part A, means from dependent samples, matched pairs. So, for example, let's take a look at this picture here, right? Now, we don't have 6 completely independent members here of the population, okay? We have here matched pairs. Let's say from here to here, from here to here, and from here to here. Maybe each blue-red pair is an individual. Maybe blue is a before measure, red is an after measure. Or maybe we have the same measures for a husband-wife couple. It could be a couples therapy program where they take a test and you have the husband score and the wife score. Husband score, wife score, husband score, wife score. So here, we might be interested in comparing the means for the two measures, whether it's the before measures and the after measures, or the husband's measures and the wife's measures. And the idea is that for each of these individual pairs, which could correspond to an individual that we're getting before after measures on, or maybe each of these pairs is a couple, it's a pair, a husband-wife pair. The idea is that we take the differences for these pairs, right? Whether it's before versus after, husband versus wife. That sounds like a great game show, husband versus wife, Family Feud. All right. But the idea is that with D here, all right, we're going to find the differences between these measures for each pair. Okay, these are matched pairs, right? These two are matched. Each blue dot and each red dot is matched. It's like a couple or different measures for the same individual. And the idea is that we're going to perform a t-test on these differences. Before, like if we're looking at the heights of a bunch of students in a class, right? We list a bunch of heights. We can take a sample mean, sample standard deviation, and do a t-test. Over here, we're going to do a similar analysis for the differences. So in a sense, it is kind of a one population, one sample problem, although it's a population of differences though, which is kind of weird. It's a population of differences. The population data. Let D be the distribution of the population of differences between all the matched pairs. Not the raw heights for the various students, okay, but the differences within each couple, within each pair. Now, the thing that we want to estimate, the thing we're aiming for, we want to test for the population mean of the differences, mu sub d. That's the mean of the d distribution, the distribution of differences. So based on the sample data, we're going to get the sample mean difference, d bar, kind of like x bar, except for differences, and s sub d, which is the sample standard deviation for the differences. N is the number of matched pairs. So over here, n would not be 6, n would be 3. We have 3 pairs. Okay, the CLT assumptions, as usual. Let's go straight to an example. We take a random sample of 3 men from the participants in a men's weight loss program. Use the sample data below to test the claim that, okay, so here's the claim. I'll put this in red. Test the claim that participants in the program lose weight on average. That's our claim. I'll start. Use a significance level of 0.05, our average. That's going to be our what? That's going to be our value for alpha, the significance level, 0.05, the usual. Assume that the weight changes of the participants in the program are approximately normally distributed. So the CLT applies. So let's say we have these 3 men. We have a before weight and an after weight in pounds. We want to know if participants in the program lose weight on average. That's the claim. Solution. First of all, calculate the differences from the table, and you have a choice. You can either take the differences before minus after, or after minus before. Actually, in calculus, you normally do it after minus before. But here we're going to do it before minus after. The idea being that if we have a bigger positive number, that indicates a greater weight gain, which in a way would be the more positive result if you're producing a weight loss pill.
Let's
ignore the side effects for now, okay? Runny nose or who knows what, right?
Yeah. So basically, if it's before minus after, that would actually be the weight loss. So weight loss of 5 pounds.
But let's say that weight loss is good in the sense that you're producing a weight loss pill. Okay, so for example, here, this person number 1, man number 1, has lost 5 pounds. Here, man number 2 has lost 2 pounds. And over here, man number 3 actually gained a pound. Still, it's possible that the weight loss pill might be effective for weight loss, but perhaps this person got unlucky in that regard. Maybe, in a sense, this is sampling error, which may not mean much to person number 3. Well, whatever. I mean, I didn't like this pill. Okay, anyway, sample statistics. N equals 3. That's the number of matched pairs. Each matched pair consists of a before weight and an after weight for 1 man. Here's the sample mean. If you work out the sample mean for this D column, right, it's going to be 2.0 pounds. Remember, we go to 1 decimal place further. The sample standard deviation is 3.0 pounds. You can get that from a calculator or Excel. The setup. Now, the claim is that participants will lose weight on average. A weight loss corresponds to a positive difference, okay? A positive difference if you go before minus after. So here, the claim is the alternative. The claim is the alternative, which says that mu d will be greater than 0. It's a right-tailed test. Remember, we write the null as mu sub d equals 0, although it technically includes other cases as well. Alpha is 0.05. Now, bear in mind that, again, a positive value for mu sub d corresponds to weight loss on average. But if we had taken the differences after minus before, then this would have been a left-tailed test. And basically, you'd get an equivalent result. Basically, your claim will be equivalent in either case. Your conclusion will be equivalent in either case if you're using the same claim. So you could do either. You could either set it up as before minus after, in which case we have a right-tailed test here, or you could set up the differences as being after minus before, in which case it would be a left-tailed test. Either is fine. Just be consistent. Okay, the methods of the lesson apply for the usual reasons, like for the t-test, except we're looking at differences. We're doing a t-test on differences. Here's our t-test statistic. The mean sample difference minus, or the mean of the sample mean of the differences. D bar here. Sample mean of the differences between the matched pairs, okay? Minus the mean of the differences under the null. Now remember, the null said that mu sub d was equal to 0 pounds. It was the borderline case of all that, okay? We're going to assume mu sub d is 0 pounds, which means this part of the formula goes bye-bye. That's often the case. The upper right goes bye-bye. 0. Over, it's like the CLT thing, right? The sample standard deviation of the differences over root n. Plug in, careful, it's a compound fraction. You get about 1.155, a t-test score, a t-test statistic. Now, using the traditional method, you could use the p-value method, but using the traditional or classical method, you can find the critical value that's involved, a t-distribution on n-1 or 2 degrees of freedom. Alpha is 0.05, it's a right-tailed test. Turns out 2.920 is the CV, it's a right-tailed test. Now, is the test T in the critical region or not? It is not. It is not. So it does not fall in the danger zone, the acid bath regarding the null. Remember, the null dies here. The null dies in the critical region. Here, the null does not die. All right. The test statistic value, the t-test score, is not in the critical region, so we do not reject the null. Is that strong or weak? That's weak. I sound like Cartman from South Park. That's weak. There is insufficient evidence. What? The alternative is the claim. It's like a research hypothesis. It's like we're researchers for this drug company that's producing this weight loss pill. We're claiming that our research hypothesis is true, that this pill works, right? So we're weighing evidence for or in support of the claim. But there's insufficient evidence for or in support of the claim that participants in the program lose weight on average. That's our claim star. So if the drug company claims, on average, our weight loss pill works. Based on this statistical hypothesis test, there's insufficient evidence. Maybe it does work, but we don't have enough evidence. Next time, what about comparing means from independent samples? Like men versus women who are single, so they have nothing to do with each other right now. That's next time.
Now again, lesson 39 is not covered in your homework, but come on, this is like a whole chapter in a lot of books. But I don't want to bore you to tears because it's just an extension of basic ideas. So in 2 videos, we're covering 1 chapter, and I'm not really doing that on the homework anyway. All right, any questions before we go on? Any questions? Let's look at more cases.
Hi, everyone. Let's say we're comparing means from independent samples from 2 different populations. So for example, let's say we have a population of men versus a population of women in the US. Let's say we're studying weights. So here's the population of weights of US men in pounds. Here's the population of weights of women in US pounds. These populations could have different means, different standard deviations. And then when we collect samples, we could have different sample sizes, which lead to different sample standard deviations and different sample means. If we're a drug company and we want to test the efficacy of a drug, then we might want to set up a control or placebo group that does not get the drug. And we could have a population, which is the treatment, or the drug group, which does get the drug. The null hypothesis could be written like this. The means of the 2 populations are equal. And look at this lovely formula for the t-test statistic. Again, the upper right is 0 under the null. That often happens. And we have a different formula for the number of degrees of freedom. Now, if we assume that the population variances are equal, then some people might use a pooled sample variance, but some statisticians warn against this. Now, one reason why researchers might want to use a pooled sample variance is that it then makes it easier to reject the null. And we have a more powerful test. So then it's more likely that you're going to basically prove your research hypothesis, the alternative. We can also talk about comparing proportions from independent samples. For example, population of men versus population of women, the proportion of men who support Senator Smith versus the proportion of women who support Senator Smith. Sample statistics, different sample sizes, numbers of successes, sample proportions, typical null hypothesis, P1 equals P2. The test statistic formula, upper right hand goes to 0. And then you have a pooled sample proportion. We can also compare standard deviations or variances, typical null hypotheses. These involved F distributions. So that's my summary of hypothesis tests for two populations.
So I have these notes online, so you can take a look at these optional notes. Again, I feel like the class would have dragged on and gotten rather boring if we had gone too deep in this chapter, because the main thing is understanding the basic idea of statistics, right? The chapter with basic hypothesis testing. For the two sample or two population studies, basically it's more complicated test statistic formulas. It might be different distributions, but the basic flavor is very similar. So you can look over this overview, but it's really the key ideas of hypothesis testing that really matter. Okay, so any questions before we go on to the required material, right? We are going to have homework on 40, for example, coming up, all right? So we did two population case in what, about 20 minutes? About 15 minutes. Let's move on.
Hi, everyone. We're going to do lesson 40 on chi-square tests for goodness of fit.
Is required.
Is this the distribution or is it something else? Now, we've actually already done a simple version of this kind of test back when we were doing tests for P, a population probability or proportion. That was back when we had binomial experiments. But now we're going to extend to multinomial experiments. First of all, let's do a review of tests for P and binomial experiments. So back in lesson 34, we discussed hypothesis tests for P, once again, a population proportion, or success probability. So for example, a binomial experiment could be flipping a coin n times, right? P could be the probability of heads, for example, on the coin. Maybe heads is a success. The null could say P equals 0.3, for example. Maybe the null says that the probability of heads is 30%, in which the case the failure probability, Q, is 70%, or 0.7. The alternative would say that P is not 0.3 in a two-tailed test, right? Now, again, this is an example, a basic case of a goodness of fit test, where you have two categories, success and failure. Two possible outcomes, success and failure. The probability of a success is P, the probability of a failure is Q. Or you could use different notation. You could say P sub success and P sub failure. And these probabilities add up to 1. So the null hypothesis would correspond particularly to this distribution. The probability of a success is 0.3, the probability of a failure is 0.7. If you don't like this for a coin example, we could have that P is the probability that it will rain on November 1st. November rain, old Guns N' Roses song. All right. In a binomial experiment, a trial, such as a coin flip, has two possible outcomes. Again, success or failure, maybe heads or tails. So now we're going to extend from a binomial experiment where you have two possible outcomes or categories to multinomial experiments where you could have more than two possible outcomes or categories. Again, a multinomial experiment is similar to a binomial experiment, except that a trial, such as a die roll, has more than two possible outcomes or categories. So in this multinomial experiment, rolling a die n times, let P sub I be the probability of a magician's die coming up I, where I could be one of the 6 die faces. The null hypothesis says that we have a uniform distribution on the die faces, meaning that the probability of getting a 1 on the head, P sub 1, is 1/6. The probability of getting a 2 on the die, P sub 2, is also 1/6, and so forth. So in other words, P sub I equals 1/6, where I takes on these various indices. So the null hypothesis says the distribution is uniform. The alternative hypothesis covers every other possible case. The distribution is different. In one way or another, the distribution is different. Whether you have a higher probability of 1s or 6s or whatever, the distribution is somehow different. It's not uniform. Once again, the null hypothesis is the basis for our calculations. Let's do an example. So in example 1, each trial has 3 possible outcomes, which we will call categories. Example 1, chi-square test for goodness of fit with respect to a particular distribution indicated by the null, which may or may not be the claim. 10 years ago, 50% of the registered voters at a college were members of the gray party. I'll go ahead and I'll put that in gray, sure. Let's put that in gray. 50% of the registered voters were members of the gray party. 40% were members of the yellow party. And 10% were neither. What's neither? How about purple? Purple's like neither nowadays, right? 10% were neither. Test a claim that, I'll put this in red. Test a claim that the party registration, well, may as well put blue. Text is blue, may as well put blue. All right, test a claim that in blue, the party registration distribution at the college is the same now as it was 10 years ago at the 0.05 significance level. Of course, that's alpha. Fishy. Now before, when we had a test for P, we could just talk about P as our key parameter. But now that we have 3 categories, we have to talk about at least 2, and we should write all 3. It's convenient to write all 3. Instead of going like, P, Q, and 1 minus P minus Q, let's do 3 good notations here. Okay, let P sub G equal the proportion of registered voters now at the college who are gray party members. So P sub G, gray party. Let P sub Y be the proportion now who are yellow party. The proportion now, not 10 years ago necessarily, but now. P sub Y, yellow party. Okay, and P sub N, proportion now who are members of neither. Okay, so 3 population parameters here, P sub G, P sub Y, P sub N. Before, in binomial experiments, we had P and G, and P and Q, and we could focus on P. With more than 2 categories, we really should have notations for all the different probabilities or proportions for all the categories. Okay, set up. See, before we just had P equals 0.5 or something, and that implied what Q was, right? Now we're indicating the hypothesized values for all 3 parameters. The null hypothesis says, wait, what did the null hypothesis say? Okay. Oh, well, what did the claim say? The claim said that the party registration distribution at the college is the same now as it was 10 years ago. That indicates a sense of equality, and that's going to be the null. The null hypothesis is going to correspond to a particular distribution. What was the distribution 10 years ago? Well, 50% gray, 40% yellow, 10% neither. So the claim here, based on the wording of the problem, corresponds to the null, which posits a particular distribution. P sub G is 0.50 or 50%, like 10 years ago. P sub Y is 0.40 or 40%, like 10 years ago. P sub N is 10% or 0.10, like 10 years ago. The note claims that the distribution now is exactly the same as it was 10 years ago. We might be going, oh yeah, isn't there probably going to be some difference? Well, remember, the idea is, are we going to reject the null or not? Do we have enough evidence against the null? Remember, the null has some resiliency here. I know it looks hard to really hit this on the mark, but in a way, in order for the nulls to survive, these don't have to hit on the mark. As far as the null goes, he just doesn't want to be rejected, right? The poor null just doesn't want to be rejected. Anyway, the claim here is the null. In other cases, the claim may be the alternative. The alternative hypothesis, H sub 1, says the distribution is different. And for these goodness of fit tests that I'll deal with you, the alternative hypothesis will always say that. The distribution is different from what the null hypothesizes. Alpha was 0.05. That was given in the problem. Now, you might be going, wait a minute. What type of a hypothesis test is this? Is it two-tailed, left-tailed, or right-tailed? Well, if you have a type of hypothesis test, well, where the alternative is saying that the distribution is different, right, like in this goodness of fit test, then that's going to be a right-tailed test, Now, before, in the test for P, different meant just the is not equal to symbol, which implied two tails. But here, actually, the tests in this lesson, these goodness of fit tests, are going to be right-tailed, which might surprise you. Okay, and I'm going to explain later on why it is that these hypothesis tests are going to be right-tailed. In fact, when you get beyond tests for standard deviation and variance, the chi-square test we're going to talk about in our class will be right-tailed. Okay. So that's the setup. I've been talking about the setup and an example here. Let's conduct the test. Let's actually talk about the sample data and what we do with it next time.
Okay, so any questions about the setup? For a goodness of fit test, the null hypothesis gives a particular distribution. Here, the same distribution as 10 years ago at the college. The alternative will say, for this kind of test, the distribution is different somehow, right? We have alpha, right? Significance level. And these are going to be right-tailed tests. Okay, and the same for the next lesson as well. Any questions? Any questions before we look at the sample data? Because we haven't even gotten the sample yet. All right, because you have to set up the hypothesis test before you get your sample data. All right, going on.
Hi, everyone. Let's continue to test the claim that the party registration distribution at the college is the same now as it was 10 years ago. That corresponds to the null, which is the claim in this wording. So let's gather sample data. We randomly sample 300 registered voters now at the college. Now, not 10 years ago. 160 are gray party members, 100 are yellow party members, and 40 are neither. Notice these add up to 300, so there are no other categories. Now, based on the statement of the sample data, we can quickly write out the O table, the table of observed values or frequencies. From the sample data, we construct a table of observed frequencies, the observed O table. We observed 160 gray party members, 100 yellow party members, 40 that were neither. That's the O table. So basically, in a problem that I give you, I would give you the information to immediately fill out the O table. But you now have to figure out the E table, the table of expected values. From the sample size, here n equals 300, and the distribution corresponding to the null, because remember, we're basing calculations under the null. As always with these hypothesis tests, we're basing calculations under the null. Base calculations under the null. We're assuming that these are in fact the proportions today. So then what would be the expected frequencies for the gray, yellow, and neither party situations? Well, remember that for a binomial NP distribution, the mean mu was given by n times p, which made sense because, for example, if you flipped a fair coin 100 times, right? If n was 100 and if p was 1/2, then the expected number of heads would be 50, 100 times 1/2. Now here we have 3 expected frequencies. For the gray party, it's NPG, 300 times 0.50, which is 150. For the yellow party, it's NPY, which is 300 times 0.40, or 120. For neither, it is NP sub n, which is 300 times 0.10, or 30. Because remember, the null hypothesis says that today we have 50% gray, 40% yellow, 10% neither. So if those proportions are reflected perfectly in our sample, then we would get exactly these values. This is sort of the ideal for the null. So if we in fact were to get these frequencies in our sample, then that would perfectly reflect the null. However, we do get some sampling error. The question is, well, could we chalk these discrepancies up to sampling error? Or are the differences between the two tables so extreme that we go, you know what, this ain't sampling error, something else is going on. We got to reject the null. Okay, as in lesson 34, we have to make sure that these values are at least 5. Bear in mind, I'm not going to trick you like that on homework or tests. And as a check, you can make sure that these add up to n, which is 300. Or another way to use this fact, when you calculate the 150 and the 120, you can subtract these from n, or 300, to get the 30. All right. But in any case, at this point, we have an O table and an E table. Now, the chi-square test statistic is going to measure the discrepancy between these two tables. The chi-square test statistic we're going to use is a single measure that will describe how these two tables are different. The test statistic. Again, we use the chi-square test statistic to describe how different the O table, based on our sample, is from the E table, which is based on the null. So again, the O table, I'll put this in blue. The O table is based on the sample data. And I give you that information as part of the problem. The E table is based on calculations based on the null hypothesis. And you can figure those out. Now, the larger this chi-square value is, the greater the discrepancy, the more likely it is we will reject the null. And that's why the tests of this lesson and the next one, in fact, are right-tailed. So again, the null hypothesis, in fact, corresponds to a situation where the test chi-square is 0. The alternative is more favored. Remember, chi-square values are never negative. The alternative is more favored if you have a higher value for chi-square, which corresponds to a greater distinction between these two tables. So here's the deal. And in fact, I have Excel to help out here. All right, so here's an Excel spreadsheet I made up. Okay, so here I've entered in the O values, the observed frequencies, 160 gray party members in our actual sample, 100 yellow party members, 100 yellow party members, and 40 were neither in our actual sample of 300 actual live voters. I hope they're live. Otherwise, we're talking Chicago machine politics. But okay, that's today. Now, the expected frequencies are values based on the null, right? 150, 120, 30. Now, the chi-square test statistic is going to be a measurement of how different these two tables are. The red table versus the blue table. I'll go through these calculations later on, but it turns out this test chi-square value based on our sample, well, based on both the O table and the E table, will be about 7.3. Now check this out. What if the observed frequencies had matched the expected frequencies? What if we had observed 150 gray voters, 120 yellow voters, and 30 neither? And look at this. The test chi-square value would have been 0, indicating that the sample would have perfectly reflected the null hypothesis. What if we had something really extreme? What if we went into anarchy? 300 neithers. No gray, no yellow. Oh, wow, look at that test chi-square. 2,700. I'm sure we're going to reject the null in that case. Okay. Over here, we're not so sure. What was it? It was, what was it? It was 160, 140. All right. Now, is this test chi-square value so big that we reject the null, or is it close enough to 0 that the null is still safe? All right. Well, we have 2 degrees of freedom because the formula, again, right tail because we reject the null in favor of the alternative for a right tail test. Remember, we reject this in favor of this, the notion that the distribution is different now. We reject this in favor of this if the chi-square test square, if the test chi-square is high. All right, how many degrees of freedom? It's not n-1, it's not 299. It's k-1, where k is the number of categories. There were 3 categories, gray party, yellow party, and neither. So therefore, it's going to be 3 minus 1 or 2 degrees of freedom, not 299. All right, find the corresponding p-value. It's a right-tailed test, so we need a right-tailed p-value. But by the way, the density curve for a chi-square on 1 or 2 degrees of freedom, it's a slide, not something like this, but don't worry about that. And what is the right-tailed p-value? It turns out to be 0.0256. The right-tailed p-value turns out to be 0.0256, and my Excel spreadsheet confirms that. That's the right-tailed p-value for this chi-square test value under 2 degrees of freedom. With an alpha value of 5%, that affects how much probability. Oh, no, I'm sorry. Alpha doesn't matter just yet. Alpha doesn't matter just yet. Okay. Later on, we'll compare to alpha. Now here, by the way, the Excel command, since it's a right tail probability, all right, then it's a 1 minus deal. It's 1 minus the cumulative probability to the left up to this value. D8 is the value, the chi-square value, 7.3 bar. D9 is the number of degrees of freedom. I put true because we want a cumulative probability, not the y coordinate up here. I don't know why you'd want that. Maybe the graph. Okay. All right. Now here's where alpha comes in. Okay, the 0.05. This is where alpha comes in. Is the p-value low? Well, is it lower than alpha? All right, here's our p-value, the 0.0256. Here's alpha, 0.05. So about 2.6% versus 5. Is the p-value low, lower than alpha? Yes, it is. The p-value is lower than alpha. The p-value is low. Therefore, the null must go away. The null must go away. We reject the null. We reject the null. Same old, same old. Is it strong or weak? Is that a strong result or a weak result? That's strong, statistically significant. We can publish it. Finally, we write a conclusion relative to the claim. We reject the null, so that's a strong result. There is sufficient evidence to say what? Well, the claim was, in this problem, the null based on the wording. Okay, the null is the claim based on the wording. All right, the null is on trial. All right, so we're weighing evidence against that null claim. Put it all together. I'll use there is sufficient evidence against the claim that the party registration distribution at the college is the same as it was 10 years ago. So let's say we take a look at these two tables here, right? Okay, so these are the values that are based on the proportions from 10 years ago, right? These are the values that we saw in our sample from today. Now, let's say the yellow party, all right? Let's say the leader of the yellow party members of the student body, all right? The yellow party members of the student body. Let's say they're saying, you know what? We think that the distribution is still really the same as it was 10 years ago. I know it looks like there's been some slippage from the 120 to 100, but we, the yellow party, we believe that at this college, that the distribution is still the same as it was 10 years ago. You can chalk this up to sampling error. Well, based on that p-value relative to that value of alpha, we're saying, if that's your claim, yellow party, if that's your claim, then no. There is sufficient evidence against that claim, okay? So you look at these two tables, there's a difference. Now, technically, the test does not formally say in which ways the differences are, but the sample suggests it, right? Okay. Basically, the statistical test allows us to conclude that the distribution now is different from it was 10 years ago, okay? We can infer that the yellow party is doing worse. Right. Bear in mind that if alpha were 1%, we would not be prepared to say that, and the yellow party will give it a pass. We'll say, well, yeah, your claim might be okay. But no, the p-value is less than this alpha. We're going to tell the yellow party, sorry, folks, the distribution is different from when it was 10 years ago. And it looks like you're losing, or you're losing support compared to 10 years ago. They've always been losing. It looks like they've always been losing. All right. Now, just a side note, where do we get the 7.333? Okay. Now, you don't have to worry about this. I used to, but you don't have to worry about this. Here's the formula for the chi-square test statistic for goodness of fit, and it'll look similar to what we see in a later lesson, right? It kind of has the flavor of variance, where you have this idea of a squared deviation. There's a rescaling, and you're adding. So it kind of has the flavor of a variance. Okay, and here are the calculations. It's the square of the deviation. So for each row, all right, it's the square of the deviation, and you divide by the e value as a rescaling. Right? So you get this from the gray party, this fraction from the yellow party, this fraction from neither. You get a 7.333. Here I'm adding the three contributions. Bear in mind, if we had gotten in our sample 150, 120, and 30, the test chi-score would have been 0, right? Because all these differences would have been 0. Okay. Again, if we had had a match between the sample and the expected frequencies, our chi-score would have been 0, no evidence against the null, none whatsoever. So the yellow party would totally be cool in saying that, hey, the distribution is the same as it was 10 years ago. Kind of like if the null posits a fair coin and we get 50 heads on 100 flips. Footnotes. What's the idea of a left tail test? And Gregor Mendel has been accused of this, the father of genetics. What if the sample data fits the expected frequencies too perfectly? Your test chi-square is just too good to be true. Then a left tail test could be a way to test for fraud. We may be concerned that the observed values may be too close to the expected values. Did Gregor Mendel manipulate his genetics data by discarding data that seemed unfavorable to his claim? Although Mendel may have thought that he had done nothing wrong. Oh, I just don't like this P. It looks funny, I'll toss it out. He may have not realized that he was conducting statistical malpractice when he was doing that. One calculation of one of his studies showed a left-tail p-value of 1 in 25,000, meaning that the probability of getting something as perfect as what Mendel got by chance relative to the null was that. His results were just too perfect. Okay, next up, chi-square tests for independence, which have similarities and differences. Next time.
Okay, so any questions? You'll get practice on the homework, of course. Any questions about that? These right-tailed chi-square tests. Okay, and this next one's also a right-tailed chi-square test, but for a different purpose. Any questions? Any questions? And again, feel free to play with the Excel worksheets. All right.
Hi, everyone. Let's do some more chi-square tests. And these are also going to be right-tailed tests. This time, we're going to talk about chi-square tests for dependence or independence. Are two variables statistically related or not? Actually, if the variables are statistically related, that's the case of dependence. Now, we've dealt with two-way frequency or contingency tables before. For example, when we talked about the tutor who was interested in working with students who were B students or C students or juniors, we've dealt with these kinds of tables before. Now, in example one, we're going to consider two variables in an election, gender and party preference among registered voters. So over here, let's say we take a poll of 700 voters. And let's say that each voter can either be a gray party member or a yellow party member. For the sake of convenience, let's say these are the only two possibilities, the only two values for this variable. Likewise, let's assume that there are only two genders, men and women among adults. I realize that's very controversial. I know on Facebook there are hundreds of genders. But let's assume that we have the two genders here. Now we're asking not so much directly men versus women or gray versus yellow. Really, we're asking more about the relationship between these two variables. Although it is true that in the 2x2 case, this really does boil down to a test for two proportions. That is actually true. All right. Now, two variables are independent if and only if there is no statistical relationship between them. Otherwise, if there is a statistical relationship between them, they are dependent. Now, that's different between causality. There's a difference between dependence and causality, and we'll talk about that later on. Also, let's quickly review the idea of independence. In both two-way tables below, it appears that gender and party preference are independent, meaning that knowledge of a person's gender gives you no additional information about the person's party preference, and vice versa. So remember, back when we were talking about probability, if I took one card out of a deck of 52 cards, and if I told you the rank, for example, this card is a 4, did that give you any additional information about the suit, whether the card was hearts, diamonds, clubs, or spades? If I just told you the rank, the card is a 4. The answer is no. Knowledge of the rank gave you no additional information about the suit. The suits were still one.
Sorry, I was trying to type in chat. Hold on, let me grow this again. Right.
So there was independence.
Let's go.
The suits were still 1/4 apiece in probability. So there was independence between rank and suit, at least on the first draw. Now I claim that in both 2x2 contingency tables below, gender and party preference seem to be independent, or at least there's no evidence against dependence. There's no evidence against independence. There's no evidence against independence. So for example, over here, does knowledge of gender tell you something additional about party preference? Well, no, because it looks like the gray party is doing very well. In fact, exactly a 2-to-1 margin in both groups, men and women, based on the sample. If I told you the party preference, would that say anything more about gender? Well, no, because the gray voters are equally split between men and women, but so are the yellow voters. They're also equally split between men and women. So this is a case where there is no evidence whatsoever against independence. This table perfectly reflects independence between the two variables. Knowledge of one tells you absolutely nothing about the other, even in just a sample. Now here, we had equal numbers of men and women, but you didn't even have to have that to be the case. For example, here, this might be the ancient Amazons. There were literally 10 times as many women as men in this sample here, okay? But still, we have independence. Again, this table here perfectly reflects independence. Because in both groups, the gray party is beating the yellow party by a margin of 2 to 1. And for both parties, with the gray party members, women outnumber men 10 to 1, but that's also true among the yellow party members. It's 10 to 1. So knowledge of the value of one variable gives you no information about the other variable and what value it could be. There's no additional information. By the way, we call these 2x2 tables. We don't count the marginals here. These are called the marginals, the row totals here and the column totals here. This is the grand total here, which corresponds to all the frequencies in the 2x2 table here. Okay. So let's take a look at this table here. Let's take a look at this table here. Wait a minute. Now, if I tell you what gender the person is, for example, if I say that gender is a man, the gender is male, well, that person is 5 to 1 likely to be for gray. 5 times as likely to be for the gray party as for the yellow party. But if I tell you the person is a woman, that person is 5 times as likely to be for the yellow party. So if I tell you the gender, that can tell you something about the party preference in terms of probabilities. If I tell you that the person is a gray voter, then there's a 2 to 1 chance that person is a woman. If I tell you that the person is a yellow voter, wow, there's a 50 to 1 chance that the person is a woman. Now, in both cases, there are more women than men. I mean, still, it's like the Amazons. There are 10 times as many women as men. Whether I tell you that I have a gray voter or a yellow voter, you're more likely that the person's a woman. But here, the margin's only 2 to 1 among the gray party members. Here, it's 50 to 1 among the yellow party members. So it matters. Knowledge of the value of one variable can give you additional information about the other variable and what value it could be. Next, we will actually discuss a particular example, setting up and conducting a hypothesis test. The chi-square test for independence or dependence. Next.
And by the way, I think you tend to see these more often. Like, for example, when you hear about the classic studies about does smoking cause cancer, bearing in mind that these are not tests for causality. Okay, it's about statistical dependence. Well, it's like you have a smoker versus a non-smoker. Did the person develop lung cancer or not? So it's like, is there a relationship between smoking and presence of lung cancer? So these you see quite a bit in studies. Questions? We're going to conduct this kind of test. All right.
Hi, everyone. Let's conduct a chi-square test for independence or dependence. Let's test the claim that, I'll put this in blue, gender and party preference among registered voters are independent in an election. So knowledge of one variable and its value tells you nothing about the other variable at the 0.05 significance level. That's alpha, the threshold for what it means to be unusual. Now, in the setup, the null hypothesis for this kind of test, whether it's a chi-square test for independence or dependence, the gender and party preference are independent. The null always corresponds to the case of independence, whether it's the claim or not, okay? the null always corresponds to independence. In this case, it just so happens that it's also the claim, based on the wording of the problem. The fact that the null is a claim is just based on the wording of the problem, but the null always corresponds to independence. Now this makes sense because remember, we're basing calculations under the null. Which makes sense because imagine this. Let's say that we have 3 machines of the same type, but they operate independently. Let's say that the probability of failure for each machine is 10% or 0.10 for the day. What's the probability that all 3 machines fail? Well, it's going to be 0.10 all to the third, right? By independence. But if I tell you that these 3 machines are connected in a network, so they're dependent somehow, well then what's, by the way, this is the probability of failure for all 3. What's the probability of failure for all 3 if we have dependence through the network? Well, I don't know. I mean, how are these machines related and how are their performances related through the network? So it's hard to base calculations under the assumption of dependence because you'd want to ask, what's the nature of that dependence? It's much easier to do calculations under the assumption of independence. Now, if we all get zapped by a gamma ray burst, well, I can't account for that. So, all right. The alternative hypothesis will always say that the 2 variables are dependent. Here, gender and party preference are dependent. Statistically, alpha equals 0.05. Our tests for this lesson, just like the last one, are all right-tailed. So we're going to reject the null in favor of the alternative if our chi-square test value is too high, if it's too far away from 0. The null loves 0. The null loves a chi-square value of 0. The alternative loves chi-square values of 1,000,000. All right. So so now we set this thing up and then we take our poll. We call up 700 voters. N equals 700, the sample size. So the sample data, our observed or O table, these are the results based on our poll. We randomly sample 700 registered voters. Okay, the sample results are summarized in this 2-way observed O table here, a 2-way frequency or contingency table. And by the way, I've copied this in Excel. This is a 2x2 contingency table or frequency table. And over here, the marginals I've put in gray. So the row totals and the column totals, these marginals are in gray. And here's the grand total of 700. These values here do not count into the size of the table. It's a 2x2 table. So here's the O table in red, same as what's in here. Now, the expected or E table, I would not expect you to compute. I would give that to you. Later on, I'll tell you how to compute these values, and these are reflected in my Excel spreadsheet over here. And yes, there are formulas, that's the hint. It turns out to be, for each corresponding cell, is basically the row total times the column total over the grand total. You don't have to know that, but that's what Excel works out. And I got these values here. So it turns out that the 2-way expected or E table under the null, as always, we perform these calculations under the null. In this case, in this type of test, under the assumption of independence. So if you assume independence between the 2 variables, party preference and gender, if you fix the marginals, so if you somehow guarantee that you have this number of men, this number of women, and this number of gray voters, and this number of yellow voters, then if there is truly independence between these 2, then these values would perfectly reflect independence. There would be absolutely no evidence against the null or independence if in fact these were the values. Now bear in mind, we couldn't observe a part of something, right? I mean, you wouldn't do that to your worst enemy, saying you're half a man. Well, I don't know, you could say that about your worst enemy, but yeah, of course, these observed frequencies would be integer, okay? The values in the E table often are not. And as before, technically, these frequencies in here have to be at least 5. I'm not going to trick you on that. All right, the test chi-square test statistic. Similar to the last lesson, we're going to use a chi-square test statistic to describe how different the O table is from the E table. It's a measure of discrepancy. And again, here are the O table and the E table. The test chi-square value is a single measure that describes how different these two tables are. How different was the sample away from what we would have expected if we truly had independence between the two variables? How different is this table in red from this table in blue? It turns out that the test chi-square value is about 1.296. I'll show you how I get that later on. That is verified in my Excel spreadsheet. Look at that formula. Woo! It uses all these cells. As an Excel challenge to you, try to pull this off for 2x3 contingency tables and so forth. You can, in principle, have these chi-square tests for 2x3, 3x2, 3x3, and so forth. It doesn't have to be 2x2. All right, but the test chi-square turns out to be about 1.296. Well, so what? What is the chi-square distribution we're looking at? It's the one on this number of degrees of freedom. We use the chi-square distribution on this number of degrees of freedom. The quantity R minus 1 times the quantity C minus 1, where R is the number of rows, C is the number of columns. Now, these tables, the O table and the E table, are both 2x2. R equals 2 and C equals 2. Bear in mind, there's a symmetry in that it doesn't matter if you have party here and gender here, or if you have gender here and party here. It doesn't matter if you make the rows the columns. It doesn't matter if you make the rows the columns and vice versa. It doesn't matter because there's symmetry. Here, we want the chi-square distribution on, well, 2 minus 1 is 1, 2 minus 1 is 1, 1 times 1 is 1, 1 degree of freedom. So anytime you have a 2x2 contingency table like this, then you're going to deal with the chi-square distribution on 1 degree of freedom. And again, we're really talking about something that you can get equivalently by doing a test for 2 proportions. Okay, so we find the corresponding p-value. It's a right-tailed test. So the 1.296 is what we got based on our sample. What's the probability of getting something at least as extreme as that just by chance if the null were in fact true? The right-tailed test, so we need a right-tailed p-value. This right-tailed p-value is about 25%, 0.2549. That's verified by the Excel spreadsheet. Remember, for right-tailed deals, it's 1 minus because you normally go left-tail. With this true deal, you're dealing with a cumulative probability to the left. It's 1 minus if you want a right-tail probability, right? So 1.2963, 1 degree of freedom, right? 0.2549, that's the right-tail p-value. Is the p-value low? Is the p-value low? Remember, if the chi-square is 0, that means the null is perfectly reflected. In fact, I'll show you that right now. What if hypothetically the E values were matched up in the O values? What if we could actually get these values in the sample? Paste special values, not the formulas. Well, looky here. If the O table is identical to the E table, I know that we can't see this in an actual poll. Okay. Who's 0.14 of a man? A really, really bad person. Okay. Yeah, the test chi-square value is 0. Test chi-square value is 0. And the p-value would be 1. If the test chi-square is 0, then you get a p-value of 1, everything to the right. Okay, but here we get a test chi-square of 1.296. Still, even though we're not getting 1, we're getting a lot. We're getting about 25% to the right. Okay, is that low? No way. No way. There's no one who's, realistically, alpha's not going to be like, 30% or something. Realistically, no. Okay, alpha's more like 5%, 10%, not like 26% or 30%. Okay, I'm sure it's going to be low. Okay, and we said early on alpha was 5%, 0.05. The p-value was 0.2549. That was the p-value. Alpha was from the problem, 0.05. 25% is way more than 5%. The p-value is not low at all by that measure. The p-value is not low. The null does not have to go. We do not reject the null. Because remember, a chi-square value of 0, like in this situation where the tables are identical, the test chi-square is 0, then that would be perfect for the null. The 1.296 is low enough, it's close enough to 0, that the null is still safe. The null is unsafe if you get a chi-square way out here, like a million. then the null's dead. All right. We do not reject the null. Is that strong or weak? That's like not guilty, it's weak. Finally, we write our conclusion relative to the claim. We do not reject the null, that's weak. There's insufficient evidence to say something. Based on the wording of the problem, the claim was the null. Put that in orange. The claim is the null, which means that we're weighing evidence against that null claim. We're putting the null claim on trial. We're weighing evidence against the null claim. Put it all together. Same old, same old. There is insufficient evidence against the claim that gender and party preference among registered voters are independent in the election.
So I think I discussed that. Yeah, I wanted to make a few final thoughts about this. Any questions before? Well, this might help some matters here. I do discuss this further. Okay, let's continue with this.
Hi, everyone. Let's think about the big picture. We said in the example, there's insufficient evidence against the claim of independence, meaning that if I claim, you know what, I didn't think there's much of a relationship between party and gender. I think these are independent. So knowledge of the party doesn't really tell me about gender and vice versa. Yes, there are more women than men, but I don't think that's reflected in the party splits like this. Doesn't matter. There's insufficient evidence against my claim, okay? So you can't really say I'm wrong. You don't have enough evidence to say I'm wrong. Okay, this table is close enough to this table. Now, just for kicks, what about a case of clear dependence? Okay, let's put in some numbers. Let's say that 500 men are for the gray party, none for the yellow. Okay, the yellow party is for making men do chores everywhere, like all the time. Okay, and then with the women, let's say that 1,000 women are for the yellow party and 0 women are for the gray party. So the yellow party is saying, yeah, make men do all the chores. All right. Well, looky here. Here's the O table. Here's the E table. The two tables, how different are they? That's a measure. Wow, 1,500. That's your test chi-square. The 1,500, that's way out there, way out there. What's the right tail p-value? Close to 0. Basically 0. All right, this is a case where it definitely matters. Oh yeah, if you're a gray party, I think you're a man. Okay, if you're a man, I think you're a gray party. Okay. Also, remember the coins extra credit? Okay, the discrimination rule. I said that I thought the people who had a run of 5 or more heads or tails, I think you actually flipped the coins and the others faked it. That was the basic idea. Well, here are the results. Okay. One variable, I said you did it versus faked it.
By the way, I should have changed the labels over here on the blue table. Right, did it, faked it. No.
You actually did it versus faked it. Here are the results. Okay. Notice I'm getting pretty strong numbers along that diagonal there. So I was making a lot of good calls. Here's the O table. Here's the corresponding E table. Test chi-square, about 8. That's out there. Okay. If you look at this distribution, the 8, that's pretty out there. All right. It's still pretty out there. P-value, right-tail P-value, about 0.5%, way less than alpha. So we reject the null of independence, which says that there is no relationship, which means, hey, this statistical test shows I'm a genius. It means that I'm definitely beating chance, okay? For example, I'm doing much, much better than if I were to just flip coins myself and say, okay, I'm gonna flip a coin. If I get a head, I said you did it for real. If I get a tail, I said you faked it. According to this test, I'm really, really beating chance. Okay, I'm really beating chance. Okay, so it looks like this rule is doing a pretty good job. All right. Key principle. Dependence does not imply causality. Statistical dependence does not imply causality. That is, just because we find that two variables are statistically dependent does not mean that there's a cause and effect relationship between the two variables. Not necessarily. Okay, so for example, look at this two-way contingency table. Pet ownership, do you own a pet or not? And how'd you score on a test? Did you score above average on a test or below average? Okay. Well, it looks like here that the pet owners, there seems to be a relationship here where the pet owners seem to be doing better, and the people who do better tend to own pets. Now, does this suggest, for example, that owning a pet makes you smarter? I don't know. Maybe there is a psychology study that says that being around a pet makes your IQ go up. I don't know. I don't know if there's a study out there. I don't think that's the case. Okay. I think there might be a confounding variable, maybe wealth or income, right? Maybe higher income families are more likely to own pets, right? And higher income families are also more likely to afford computers, additional resources, tutors, books, and so forth. So you might have a compounding variable like wealth. Sorry, not compounding, it's confounding. A confounding variable like wealth. Okay. A confounding variable is a factor that we are not considering that is affecting both variables in the study. Here, a confounding variable could be income level, which could have a causal relationship with respect to both pet ownership and higher test scores. So income could affect both of these, okay? But maybe it's not so much going this way or that way. And by the way, how are the E values calculated? Okay, well, basically, if you look here, the marginals are the same, right? The marginals are the same in both the tables. Basically, the idea is it's going to be row total times column total over grand total. So if you look at the O table, right, it's row, like for the first cell, the upper left cell here, how do you get the E value for the upper left cell there? It's the row total times the column total corresponding to that cell times the grand total. And it comes from independence. For example, the probability of men and gray, all right? Under independence, that's the probability of men times the probability of gray, right? Under independence, these probabilities split up. So the expected frequency will be n times the probability of men and gray, which is n times this product under the assumption of independence. If you work out the fractions, you get that formula. Okay, the formula being row total times column total over n for each cell. And then you have this variance looking thing, right? The square deviations are rescaling some of those. Chi-square distribution on this number of degrees of freedom. And these were the numbers that led to the Excel result. Okay, well, up here. $1.2963. Again, for a 2x2 contingency table, it's similar to a test for proportions for independent populations. Okay, next up, more topics.
Yeah, the next one's a short one, and then okay. So let me describe where we're at. There are two more lessons for today. Now, the next one I'm going to spend a minute and a half on Anova. Anova is a huge topic. Okay, I'll show you this here. Yeah, so Anova analysis of variance is a huge topic, and it's optional. There's no required homework on it. but it is part of our curriculum. So what I want to do is, last week I found some nice videos on Anova, and just for your own study, especially if you're entering the social sciences, because they have some SPSS output, there is at least one video I'd like you to look at to give you some background on Anova, especially if you're going on to a social science stats class where you might have to use SPSS. Well, SPSS is the key. It's like a statistical package for the social sciences. So I do encourage you to look at the Anova video for your own personal benefit, especially if you're in the social sciences and you're going to take an SPSS class. So I just want to take a minute and a half to discuss Anova. Just kind of listen to this part here.
Hi, everyone. Just briefly, I want to discuss lesson 44 on Anova tests. This won't be on your final or homework. Now, even though Anova stands for one-way analysis of variance, really it's used to analyze means from 3 or more populations by using sample variances. So the null hypothesis looks something like this. So that we're testing for the equality of means for multiple populations. The alternative says that not all the means are equal. A two-way analysis of variance, a two-way ANOVA, is more complicated. It uses 2 factors, variables such as gender and party preference, like we saw in lesson 41, maybe to analyze values of a 3rd variable, such as income. But then we should first test for an interaction between the 2 factors, like we did in lesson 41. Is there a relationship between gender and parity, okay? If there's an interaction effect, if there's a dependence there, then that would compromise our ability to perform a good statistical analysis on the main effects between just, say, income and gender, or income and party alone. All right, next up, correlation and regression. Oh, and by the way, with these things, the F distributions are usually involved in analysis.
So again, maybe tonight I'll email out a link to at least one pretty good video on Anova. I looked at several Anova videos last week. I think there's a best one that I'd like you to look at some point, and then there are others that are a bit more technical. But there's at least, I think the best one does give you a good overall summary of the F distribution and Anova. Okay, but that's all optional. This next bit on correlation, that's required. And this is the last video for today. We'll continue on Wednesday.
Hi, everyone. Lesson 43 is on correlation and regression. What is the relationship between 2 quantitative variables, and how strong is it? So let's consider scatter plots, which are used to graph paired data, or bivariate data, which involves 2 variables. For example, midterm 1 score, comma, midterm 2 score. N pairs of scores for N students. In fact, what you see here is a scatter plot based on an old version of Minitab, midterm 2 score versus midterm 1 score for about 90 students in a class. This person didn't do so hot. This person got a 25 on midterm 1 and a 12 on midterm 2. We'll come back to this. Correlation. Rho, that's a Greek letter, is the linear correlation coefficient for a population of bivariate data. R is the corresponding sample statistic. These measure the direction and strength of the linear relationship between 2 variables, and they're sometimes named after Carl Pearson. The following properties apply to both Rho and R. Assume that we have bivariate data, pairs of this form. The linear correlation coefficient is a number between -1 and +1. The absolute value of R, meaning ignore the sign, measures the strength of the linear relationship between X and Y. So for example, 1 and -1 indicate the strongest possible linear relationship. The sign of R measures the direction of the linear relationship. If R is positive, then Y tends to increase with X, like positive slope. If R is negative, then Y tends to decrease with X. If R is 0, then there's no linear relationship between X and Y. A typical hypothesis test would involve the null hypothesis saying that Rho is 0. Again, no linear relationship. So let's say that midterm 1 and midterm 2 represent test scores. Let's say that X and Y represent test scores. X is midterm 1, Y is midterm 2. They both have mean 50 points and standard deviation 10 points. And let's look at various values of R for these various scatter plots. Here, R is 0, a big old blob with no linear relationship. R equals 0.4, kind of a rather weak linear relationship, but generally going up. And stronger, 0.9, 0.95, stronger linear relationship. And by the time you get to R equals 1, you get a straight line. Likewise, if you go negative, okay, you get a stronger linear relationship as R moves away from 0, and in this case towards -1. But in this case, in these cases, since R is negative, the scatter plot is generally trending downward. By the way, in order to standardize pictures that will help you compare correlations, it helps to make the length, it helps to make one standard deviation on the x-axis one length, and the same length being the length of one standard deviation along the y-axis. So basically, one standard deviation on the x-axis should be the same size of one standard deviation on the y-axis to get good comparison procedures. Over here, the scatter plot I showed you, rho, the population linear correlation coefficient, was only a 0.4, which was shockingly low, but it revealed something about the class. And in fact, this class was massively restructured since then. Midterm 2, the material on midterm 2, had almost nothing to do with the material at midterm 1. The midterm 2 material did not build up on the midterm 1 material, which explained this rather cloudy nebulousness. Rho was low. Rho was low in absolute value. It was only 0.4. It was surprisingly close to 0. Normally, when I was at T at UCSD, the midterm 1 and midterm 2 for a calculus class would give us a rho of about 0.8 normally. But this showed us perhaps a flaw in the course, which was that the midterm 2 material did not build on the midterm 1 material. Again, like statistical dependence, correlation does not imply causality or cause and effect. You could have, for example, confounding variables. R might not pick up strong nonlinear relationships. For example, here, you might not pick up a good nonlinear relationship. If you go to Wikipedia, here are examples of scatter plots where you get correlation coefficients of 0, even though there are patterns in the data, not just a big old blob. Averaging tends to inflate the strength. Like, for example, if you take the average dorm scores within, if you take dormitories and take average test scores by the averages in the dormitories, okay, so you have one average score for each dormitory, that tends to inflate this here. Next, we'll talk about the linear regression line.
Okay, so as far as the correlation goes, a lot of it was about those pictures that I was showing you. Okay, do you have a sense of
Everyone,
like for example, what kind of picture would lead to more of an R or rho value of a very negative value, closer to 0, closer to +1, and so forth? Okay, so for example, here, positive values of R or rho. Remember, R is a sample statistic. Rho is a population parameter if you have all the people in the class. Okay, so here are positive values of R. You have a general linear trend up. And for the negative values of R, very negative values of R, you have a general linear trend down. But that's the kind of thing I test on, right? Kind of getting a sense of what these values of R or rho could look like. I'll talk about this stuff in greater detail on Wednesday. Otherwise, it's too much packing in for today. I think we've done enough. All right. So at 9:34. Okay. So technically, you have enough to do almost all the homework. Okay. You have enough to do almost all the homework. Okay. Lesson 43, I'm still working on. Any questions so far? Any questions? So you can do almost all the homework at this point. I'm going to continue with correlation and mostly regression on Wednesday. And I'll start discussing the homework on Wednesday, continue the homework the following Monday. And the homework's due on Tuesday of next week. Okay, any questions? Any questions? All right, so I'll pause right